Folks, morning. Um, Monday morning here. Hope your weekend was good. You were able to weather that was out there and all that good stuff. Um, Thank you for the vast majority of you taking your quiz. Results were really, really good. Averages in the mid 90s, which shows that you folks are doing real well with this sound stuff. So that is really, really good. So kind of a week at a glance for you. Today we're going to talk standing waves. Tomorrow I'm going to talk interference and beats, which will be pretty interesting for you, I think. Wednesday I'm going to do a lab. I'm going to do the 16.2 lab with you. I may also try and find another one for you just so you can see what that one looks like too with tuning forks and stuff like that. Thursday we'll do in-class review together, and then Friday we'll take that test for this chapter. Then we'll be on to light next week. Okay. Like I said today we're doing standing waves. Standing waves are kind of interesting. You probably, if you've ever picked up a guitar, um, seen standing waves at least there. If you've ever looked at the inside of a piano, and seen how those strings work there, you'll also have seen likely the concept of a standing wave as well there. Okay. All right. So here we go. Okay, so standing waves. So in lab from last week, when I sent a single wave pulse down that string, right? What we saw was it started on top, right? So because it started on top, when it hit the end, what took place was I had it fixed. What that means is that it was anchored to a shelf for me. All right. That meant that the energy went from the top once it was going in, and then it hit and did what? It should have went down to the bottom, right? So it bounced off the barrier. Now, if you're ever interested in seeing standing waves, what they do is they'll have some that are attached not to a fixed point, but to a variable point that allows it to move. And so what happens is you snap that wave goes in, it hits that variable point, and then it just comes right back through on that top. It's kind of wonky, kind of funny. But for us, because I had a fixed point, all of that energy on the top is going to hit and drop and come back down to the bottom. Right? So it did bounce off of it and come right back towards me. Okay. So the question then becomes, what if we send a series of wave pulses down the spring? Right? So if you start to send a series of wave pulses, again, and this is like in that guitar string, or if you've ever had a rubber band, right, and you just keep plucking that rubber band, what you're going to see is those pulses start to go consistently, right? If you can get the um, method of it or the rhythm of it to be the same, now the pulses start running into each other. Once they start running into each other, depending on how consistent you can be and how clean you can produce this concept of a standing wave. Now, if you get kind of off a little bit, then what happens is that there starts to be some jaggedness in it. And I'll show you this on Wednesday. Okay? So then we ask the question, what happens when wave pulses run into each other? Well, if they're going to run into each other, what that means for us is that we should get some form of interference. Remember the two types of interference? Oh, constructive and destructive, right? So when we have those two, those are our two forms of interference that we're going to see, right? So what does it look like when they meet crest and then it runs into another wave crest, right? Yeah, you should get a bigger wave, right? What happens when it's trough to trough? Yep, we should also get a big wave here too. But now this is going to be a big trough, right? Now, this is the one that's a little bit different. Can't remember if it was on the video I shared with you, um, but they talked about some sailors had seen like really deep holes in the ocean, and there again, that's where instead of that rogue wave hitting, it's like a rogue trough hitting, and what you see is you see this depth of this of almost like say I would say a whirlpool without the spin, but you just get this deep trough that all of a sudden causes these ships to go way down into the water and stuff like that, right? So what does it look like when a wave crest runs into a wave trough? Right? Well, it should cancel each other out, right? So just to highlight these two, the top 2 points, those are what again? Yep, you're right. Those are constructive, right? So those are going to be our constructive interference where we have same point hitting the same. The crest and the trough at the bottom, that's going to be destructive interference. That's where you're going to see stuff start to cancel each other out. Okay? When two waves of equal frequency interfere, and their crest will always meet a trough, and those waves will always cancel out. So, like you saw in the first slide, as I started to move that green wave through, all of a sudden now we started to see that change here, right? So you can see my resulting kind of black wave there, right? It's the result of the red and the green. Okay. Now, when done correctly, you're going to get nice clean waves like this. You'll have a definite maximum amount of constructive interference, and that maximum constructive interference is when that trough and that crest are so far apart, right? You're also going to get a maximum destructive interference. That's when the black line is just flat, right? Everything's canceling out. So as these two waves are moving against each other, what we're going to see is that creation of a crest and a trough. We're going to get constructive interference. We're going to get destructive interference on that whole thing. Okay? Now, the location where there is always a cancellation, meaning that the point where it always seems like there's an X, like it's either going up from that point or it's going, down from that point. That's called a node. So what we see is those are all the different nodes we have in this standing wave. Okay. We've got what, 1, 2, 3, 4, 5 different standing or 5 different nodes there. Okay. If you wanted to, you could also say the area in between where the maximum kind of crest or the largest trough is going to be, it's also called an antenna, right? That's where that biggest shift is going to be for us. Okay. Um, so if we look at this one here, right? Oops, sorry. Okay. What we get is we get just a picture of that, just a breakdown of it so that you can see. In the top one, right, we get our antinode, right, where we're talking about, right in the middle there. Okay. So what we start to see is that this area here, okay. So what we start to see is that in this point here, right, that's our antinode. Okay? In this point here, that's our node. As we start shifting it a little bit, right, what starts happening is we start to see that changing. But one thing to notice is that no matter where we go, node, that node tends to be in the same spot. Even if we look at this one here, that node is still in relatively same spot. Okay? Because those waves are going to be traveling at the same rate. Once we get 180 degrees out of phase with each other, and that's what we're going to see is we're going to see that node, that node, that node. Okay? So then what we're able to do is we're able to see now, okay, that combining them back together, we're able to see movement out of it. Okay. And again, here, our wave speed is directly related to that frequency and that wave. How fast is that wave traveling? Right. So what we see is this is half a wavelength. Now this gets really, really weird. Right? And the reason that this gets really, really weird for some people is because when we look at this one singular point here, right? What we're going to see is this part here doesn't have both aspects of the transverse wave. Doesn't. Meaning the resultant wave that we're seeing there all we have left is either a crest or a trough. We don't have both of those. So because we don't have both of those, that ends up meaning to us that we would have to go to the next node to get a full wavelength. Right? Out there, that would be how many wavelengths? Well, if you're counting nodes, half, that's one, 1.5. It should be 2 wavelengths. Okay? Based off of that, that's how we start to see it. Okay, and again here, I'll see if I can catch us at the right point for us. All right, what we're talking about here now is in this one wavelength here, we've got a trough there, right? And we've got a crest here. We have both aspects of the wave. Right? Out here, you're going to see the same thing. We got a crest there, and we got a trough right there. Sorry. So that's how we're able to designate that that is one. And because we've got 2 crests and we've got 2 troughs, then what we're going to see there is that we have 2 wavelengths. Okay? All right, pretty easy day for us today. I just want you to go watch this video. All right, it's about a 2-minute video. Gentleman is going to play guitar. I think he put his iPhone or his phone inside of the guitar and shooting out. So what you can see is you can see the actual standing waves. It's pretty fun. I think you'll actually find that one to be kind of interesting. All right. Otherwise, that's really it for the day. If you have any missing work or any outstanding homework or labs or stuff like that, use today to get that stuff done and turn it into me. All right. I will go through a bunch of that stuff and start to put in any missing work that I have today. I also want to get that done before the end of the week so that I can give you an accurate view of what your grades look like. Okay. Otherwise, folks, have an absolutely fabulous day. Hope you're doing well. Make sure this week early on, at least, you get out and enjoy some of that warm weather, especially Wednesday when it's really nice. Okay. Take care. Talk to you. See ya.